All right, let's go through a Hello World Kubetorch example. So what I have here is a vanilla training script. You could think of it as something that I just pulled from an open source training framework or vibe coded or found in my team's Git repo. But the important things to note are that it uses CUDA and distributed data parallel, meaning that I'll want to run this on cloud compute because I don't have multiple GPUs attached to my laptop, unfortunately. And it uses PyTorch, but actually Kubetorch is not PyTorch specific. We call it Kubetorch because it takes inspiration from a particular PyTorch API that you'll see below, but it supports running arbitrary Python on essentially arbitrary cloud compute and other distributed frameworks like Ray, etc. So when I actually want to run this, if I weren't using Kubetorch, would be to make it so that I could launch it from some kind of CLI command, like using a system like argparse or Hydra or something like that. And then that would represent essentially one replica of my program. And if I want to run it distributed, I need to run multiple replicas. So I would need to then take this and build it with like a Dockerfile and deploy it with something like a Kubernetes resource YAML. If I were using Kubernetes, or if I'm using SageMaker, I deploy my replicas with SageMaker's magic incantations, or for Slurm I would use SBatch, etc. And that introduces human process outside of my script. So it hurts reproducibility, adds more manual labor. It's a lot harder to debug because I have to go and retrieve my failures and hunt them down. And when they fail, when the job fails, the environment has essentially disappeared. With Kubetorch, I don't have any of these problems. I can modify my script in place and keep all of the infrastructure configuration in code, and I don't have to worry about all those magic incantations, the opinionation those distributed systems add. So to run this on distributed compute in Kubetorch, I just specify the compute that I want to run my training on. So in this case, cursor knows what I want to do because it's looking at the other files in this repo, but I'm specifying that I want to run this on one GPU, so that represents one replica, and I could specify lots of other shapes of compute. I could say CPUs, disk, memory, types of GPUs, etc. It's basically just a resource request up to my Kubernetes cluster, but that's an implementation detail you don't necessarily need to think about as an ML engineer. And then I specify the image that I want this to run on, and here I'm using a public PyTorch image. I could use my team's private image. I can also lightly modify this and add like pip installs or additional setup commands that I could add into a Dockerfile, but I wouldn't actually, if I were using Kubetorch, have to rebuild that Dockerfile. If I make those modifications here in code, we'll actually automatically patch them in. So that's a pretty nice interactivity feature. And then I want to distribute my workload to 4 workers. So I specified 1 GPU for single worker, but I want to run this distributed, so now I'm basically replicating to 4 workers. And because I was using PyTorch inside of my program, meaning PyTorch distributed inside of my program, I want to make sure that those workers have PyTorch distributed communication wired up between them. And Kubetorch will do that automatically. If I'm using Ray, I could specify Ray here. And if I were using Lightning or Hugging Face Accelerate or other things in the PyTorch distributed ecosystem inside my program, they would work as well. And so now I just take my train function and I call .to, this is the part that's inspired by PyTorch, my compute, and this will actually deploy it to Kubernetes on the fly. And what I get back is a callable that looks exactly like my original train function, meaning it takes the same inputs and returns the same outputs, and it will stream back logs and propagate exceptions, but it's actually RPCing my request over to my distributed replicas on the cluster. So now when I modify my training script to use this new function and I call it, it's actually calling directly in Kubernetes. So let's actually see what that looks like. First I need to save this out, and I'm going to run my script. And so what's happening now is it's actually deploying to Kubernetes on the fly. And you can see my 4 pods already. These 4 pods are the 4 replicas of my training. And my ranks have all connected. But I hit a bug that I intentionally added into my code. I added an extra S and loss in my script. You can see Kubetorch actually just propagated the traceback right to me, which was very nice compared to going and checking on the script and retrieving the logs from elsewhere. But let's fix the bug. And so here is like the real magic of Kubetorch. I just fixed this bug. If I were running through Kubernetes or Slurm or SageMaker or whatever else, any other way I could be running Python on cloud compute, other than let's say like a notebook or a dev box where I can't actually do distributed. I don't have the compute scale. I would have to redeploy. I'd have to basically rebuild and redeploy and go through all that human process again to check that I've actually fixed this bug and continue on with the development and debugging process. Even if I have automation in place that does that for me, I still, once I hit that error, if I were using Kubernetes or SageMaker or something, I nuked the entire environment, and now I need to just fully recreate it from scratch. So even if there's automation, it's still going to take me 20 or 30, sometimes 60 minutes. Those are typical wait times that we've seen to just do a single iteration in your code. In Kubetorch, that iteration takes about 1 to 2 seconds. So you'll see that I just saved out my file, I reran my my script, and in the 1 to 2 seconds that it took to that you just saw here, it actually hot synced my changes up to the cluster, and now I'm actually watching the training and watching my silly loss function that doesn't go down, but I was able to actually iterate and debug this with 1 to 2 second iteration, which is pretty unheard of in ML. It's 100x faster than what you could get any other way. I can even use other forms of interactive debugging, like I can call KT SSH into one of my replicas, and I can specify any replica, and then I can just do typical debugging activities. I can port forward. I can even use a live PDB debugger inside of one of the remote training processes, which is really unheard of. But the point of Kubetorch and the point of all this is to show you that my development and iteration loop is now fixed. And because I ran this from local Python, meaning I'm using a completely regular IDE. There's nothing special about it. I can use any IDE I want. I'm running from just a regular Python interpreter. I can run this exact same code from anywhere, meaning, in principle, I could be running it from inside of a notebook or wherever I like to actually do my active development. But that also means I can run it from CI, and it also means I can run it from wherever my production environment is. So if my production environment is running this inside of like an Airflow node or inside of a fast API app, I don't have to modify my program whatsoever to run it in production. The research and production loop is completely closed. So this Python code, let's say I wrap this in an Airflow node and I'm running it in production, or if this is already running in Airflow and I want to fix my iteration debugging loop, I take that code and I modify it to run it with Kubetorch. So then when I redeploy it into Airflow, it's going to run exactly as it did when I ran it locally on exactly the same compute. Let's say now that it's running in production, something breaks, or I want to just change something. I want to try a different model architecture or something like that. I can take that code as is that's running in production out of my team's Git repo and modify it and run it and iterate it and debug it locally, just like any other software engineer would for their code, right? And the rest of the software engineering world, if you wanted to change something about code that's running in production, you can just locally modify it and then push up your changes, and it takes very little time at all compared to ML research to production, which can take a quarter or something like that. So we've not only fixed the iteration and debugging inner loop, we've also fixed the outer loop just by making it so that all of this fits into regular vanilla Python. There's no local runtime. There's no magic CLI start command or anything like that. So that's Kubetorch. If you're interested in trying it out, please let me know. Thanks.